Good morning, good afternoon, and good evening. No matter what time zone you're joining us from, it is my great pleasure to talk to you today about our briefing on effective vulnerability discovery with machine learning. I'm Asankhya, and this is joint work with my colleague Ming Yi from Veracode. In this talk, we will talk about vulnerability discovery. We will see how finding vulnerabilities in your application goes beyond the code that you have written yourself. If you look at any modern software application, it is composed of a number of third-party components and libraries. The increase in the number of libraries means that your application today has a much wider surface of attack. In this presentation, we will discuss about ways in which we can curate and track these vulnerabilities at scale. Just a brief bio about us. I'm Asankhya. I'm the Director of Engineering at SCA, which is the Software Composition Analysis Product Group at Veracode. I'm joined in my talk with Ming, who is a Senior Research Engineer also working at the SCA Product Group at Veracode. Our agenda for today has 3 points. First, we will talk about the problem of vulnerability curation in the context of software composition analysis. Then we'll discuss about our machine learning approach, which is used to identify these vulnerabilities. And at the end, we'll talk about what it means to be effective at doing vulnerability discovery at scale. So what are some of the difficulties in tracking down these vulnerabilities? If you look at the number of libraries and components that are used, they have exploded in the past few years. Today, developers have a choice of downloading millions of libraries from third-party repositories. It becomes very difficult to keep track of vulnerabilities that exist in these third-party libraries. So we need a way in order to curate and collect the vulnerabilities that are found and rely on some sort of a vulnerability database when we analyze these libraries and applications. How do we curate these vulnerabilities, right? So we process data from a variety of internet sources, including the NVD or the National Vulnerability Database. We track the upstream software artifact repositories of all open source libraries. So these include things like their bug reporting systems like Jira, Bugzilla, GitHub Issues, or their source control repositories like Git, Bitbucket, etc. We do that because we realize that even if there is a vulnerability that eventually gets assigned as CVE, there is a high likelihood that there are clues or hints about that vulnerability which are available in the upstream software artifacts of these repositories, where you could actually track them much, much earlier before they eventually reach the NVD. And in case of open source libraries, many of the vulnerabilities and security issues still do not get assigned with a CVE. Now, when we started this process, we were doing things manually, and we realized that it is extremely difficult. And the reason for that is we have to support millions of libraries. We actively track thousands of Git repositories. And in order to manually do this means that somebody needs to sit in and take a look at every single commit message or a bug report that is filed, and then make a judgment to see whether it's related to a vulnerability or not, right? And once you know that it's related to vulnerability, you still have to do further investigation to figure out what versions are affected, what is the fix, and how do you address that vulnerability. So we need a solution that can scale with the increase in the number of libraries and third-party components. So it's quite natural to think about using machine learning in this context, because if you look at it from a perspective of machine learning, this is like a classification problem. So you have some particular data source, whether it is a bug report or a commit or mail advisory, and you want to figure out whether this is related to a vulnerability or not. So you have like a binary classification problem, right? So when you look at it from a machine learning perspective, you'll realize that the data set that you're dealing with is highly imbalanced. So the chance that a given commit out of all possible commits is related to a vulnerability is actually very, very low, right? So when we looked at our own data, we realized that depending on the data source, even after doing some pre-processing or removing, some obvious things or filtering obvious candidates, we ended up having a data set which is highly imbalanced. So in some cases, it could only less than 6% of the data set was related to a vulnerability, right? And as we continue to expand on the different sources, or we continue to add more libraries to our system, the size of the labeled data set keeps increasing, but the unlabeled data set is always there. So imagine you start using the system and then you start predicting what items are related to vulnerability. Eventually, you will have a system where you're always doing positive class predictions. And over a period of time, your labeled data set will only consist of positively predicted data because you're not really verifying or validating the things that are predicted to be not a vulnerability, right? So that's the whole point. So you want to scale. So you end up having a data set which is labeled, it's highly imbalanced, and the labels are mostly related to the positive predicted data set, right? So due to these two problems, we really needed a solution that can balance and scale the system despite having these two issues. At this point, I would hand over to my colleague Ming, who would go over about and talk more about our approach towards vulnerability curation, which is based on machine learning. Over to you, Ming.
Thanks, Asankhya. As noted previously, we wish to develop a process to hunt for vulnerabilities at scale. So we iterated on our machine learning approach that is able to keep up with our requirements and scale. The following section is a condensed summary of the machine learning approach we presented at the Mining Software Repositories 2020. In this new approach, we incorporated more data sources and supported more programming languages. On top of that, after having the system run over a period of time, our data has become highly imbalanced. The highest imbalance from our most affected source went from about 6% to about 3%. What this means is that if we looked at 100 items, we would not utilize the other 97 of them. This became an issue as it can cause the machine learning model to be overly biased depending on the machine learning parameters we desired. To solve the issue of data imbalance, we introduced self-training into our machine learning approach. The self-training approach allows the machine learning to utilize the unlabeled data for training. This is particularly useful for data sources that display a huge imbalance of labeled data proportion, such as for commits. As Asankhya mentioned earlier, in a machine learning system, we will want to be able to only focus on the data that matters. And so, the majority of the data we process comes from the data that were predicted to be vulnerable. However, as a machine learning model is usually imperfect, there will be type 2 errors where it provides false negative predictions. Together with the false negative predictions, we also have a portion of data which have never passed through the initial filter. These two types of data makes up the unlabeled data which will be utilized for the self-training approach. Through our evaluation, we find that the new model is generally perform no worse than the old model, and in most cases, we did see an improvement of performance from the new models with self-training. From this study, we also made a couple of observations. Self-training generally increases the dataset which the model is trained on, and the increase of performance diminishes as if we test it on models which originally have a high recall rate. Overall, we have deemed the study to be a successful one, and throughout the rest of the talk, when we talk about discovering vulnerabilities, it is generally from processing data that we have put through our machine learning model. So up until this point, you have heard about vulnerability curation and how machine learning has been utilized to help us discover and curate vulnerabilities. However, it's time to take a step back and wonder why all these are necessary. Why are we even doing this, and to think about what we are trying to achieve, to understand about the complexity of this issue. Moments ago, you have heard about how we have implemented a machine learning solution that enabled us to process data at scale, with the main goal of finding vulnerability-related data from the entire stack of general data. It is shown to be efficient at finding vulnerability related data. However, it does not automatically translate to data we are interested in. So what exactly are we looking for and why? At this point, you may even be asking me, hey Ming, isn't there a ton of databases and central authorities we could use to help identify these vulnerabilities? Well, before I get to that, first allow me to provide some context and motivation behind why we are so interested in discovering vulnerabilities firsthand. To help understand some of the motivation, we will learn about the nature of modern software composition before moving on to the topic of dependencies, and finally to highlight some inefficiencies, in particular the central authorities. As we will see in the next few slides, the problem of securing today's software is not as simple as we would like it. Let's relook at how we typically think of securing our code. First, we start off with ensuring that developers adhere to safe coding practices. Then we run static analysis to further ensure our first-party code will be relatively free from well-known vulnerabilities, such as SQL injection or directory traversal. We might even run dynamic analysis to check if we might have missed out from detecting some subtle bugs, or to reach code that static analysis would not be able to fully understand. To double down on finding exploitable vulnerabilities at runtime, we can also conduct penetration tests. And if we have done everything up to this point, our code is relatively secure. What else could go wrong? Well, an often overlooked point is the threat of external dependencies. When you use external dependencies, you are subject to both the good and the bad part of it. The threat ranges from regular code flaws to malicious threats that tries to hide itself through pre-install, post-install scripts, or even through social engineering attempts, such as typo squatting. The threat of external dependencies is not just about what kind of threats are out there, it is also about how it is increasing our attack surface without us knowing about it. Just in the picture on the right of this page, describes a regular expression denial of service issue found in URL regex. If you take a closer look on the fifth row where it says path, the URL regex package is actually not directly being used by this application, but it is found in the sixth layer of dependency. Hopefully by highlighting this example, you would have a better picture on how the issues can go unattended and how it can actually go dangerous. Now that we have discussed about the potential of a dependency causing harm, let's look at the nature of modern software composition. Most software built today are almost always built with a ton of third-party dependencies. Very few of us would write our own framework or even a HTTP request client from scratch, just to implement a feature that may take a few hours or a few days to write. To give a quick overview of modern software composition, I used some key information from Veracode's latest volume of the State of Software Security report. Depending on the programming language used and the type of application, a real-world application would typically include tens to hundreds or even over 1,000 third-party libraries. When you have such a large amount of third-party libraries being used, most of the code in your application would most probably not consist of your own code, but would instead mostly consist of code that others have written. This code may not be audited by anyone, and it would also be too expensive to run static scans on the entire applications if your application is pulling in hundreds to 1,000 over third-party libraries. The top 10 used libraries in JavaScript is included in over 80% of JavaScript applications. Well, one way to look at this is if any of these top 10 libraries was vulnerable, it could cause most of the JavaScript applications to be vulnerable. In fact, we found that at least 2 of these libraries in the top 10 list have had known vulnerabilities at some point. In a study of all applications scanned over a year, over 70% of applications tested has at least one external library flaw, and of which over 40% of these external libraries were not directly requested by the developer. Again, all this just shows how widespread the issue could get when developers use third-party libraries in their application. How about relying on central authorities? When it comes to the topic of central authorities, while we agree that central authorities provides validated vulnerability information, the issue arises when they are overly relied on to provide the source of truth of vulnerabilities. So the issue of central authorities include the time taken for vulnerabilities to be published, the inaccuracy of the data, where information could suggest that all versions before a certain version is affected. But it's usually not true, as the vulnerability may be introduced only at a certain version. Imprecision of the data, where information could suggest imprecise software component. An example would be like if Spring Boot was stated to be vulnerable, it is usually only a specific component within Spring Boot. The inaccuracy and imprecision of these data generally causes it not to be directly actionable. Furthermore, there are flaws which are not found on central authorities. The percentage of such flaws varies per programming language, and the overall average was found to be at 15%. With respect to understanding what your application is vulnerable to, one of the gaps would be to only rely on central authorities. When we look at how software is built into this landscape, to develop the intuition of discovering vulnerabilities in third-party libraries, we will need to also understand the challenges with finding such vulnerabilities. 2 main challenges arises. Resources are limited, and new libraries or library updates are usually many and frequent. Therefore, we find that as a starting place, we wouldn't recommend to directly look for vulnerabilities in third-party libraries. After all, we don't really know what we can expect to find and would not know where to look from. For the remainder of this talk, I will not go into the details of collecting the precise information of vulnerabilities. Instead, we shall focus on the vulnerabilities themselves and how we can discover vulnerabilities. So instead of the traditional way of securing code, such as using static scans, we could look for sources where the developers and contributors will interact. Data sources such as GitHub, Jira, and mailing lists are very rich in information to know the good and the bad about a particular library. And to test our intuition, we have formulated a process to help us gather these data. However, doing so also results in an infeasible large dataset in the 100,000s range per week. For this reason, we implemented the machine learning approach that reduces this amount to thousands per week. To talk about the results of this implementation, I will be sharing some data examples in the next few slides. First, we have a case of denial of service found in the Axios package. The issue here is where Axios streams will not be destroyed if it exceeds the value of max content length, and having lots of them would lead to high CPU usage, thus causing the denial of service. Normally, this wouldn't be such a huge issue. However, Axios is downloaded over 13 million times a week and is depended on by at least 44,000 others. This example highlights the potential for issues to be highly widespread. Next, we have an issue of denial of service through regular expressions, found in the trim package. This example also highlights on the potential for issues to be highly widespread. The package is downloaded over 3.4 million times weekly and is used in over 371,000 repositories. If we look closer in the picture, we can see that the issue was still being left open and was at least 7 days old when the screenshot was taken. For such a widely used library, the time to react to such issue may result in a more severe penalty. Cross-site scripting has been consistently one of OWASP's top 10 vulnerabilities. Here we see a particular case of found in XXL job used by over 2,000 repositories. This issue isn't going to reach as many end users as the previous two examples, but it should not be left alone as well. The OmniAuth package is vulnerable to cross-site request forgery, and it is rated as a high severity issue by NVD. OmniAuth is a library that provides flexible multi-provider authentication for web applications, and it is typically used in Ruby on Rails applications. While the issue is only present in specific conditions, it is rated as a high severity issue as it can allow an account to authenticate as another account. A Ruby on Rails application could likely use the OmniAuth library for authentication in the unsafe manner and have this flaw baked right into the application. In this specific example, we can see that a warning has been added to the README, and it was not addressed directly in the library. A possible reason might be due to the flexibility attribute of the library. Here's an attempt at security by obscurity in Zen CLI through a one-word description patch. The issue was caused by a weak regular expression that could not properly sanitize file paths. These are some of the data points where we think that the machine learning approach shows its efficiency at discovering vulnerabilities at scale without the need to run any form of static or dynamic analysis. An issue of arbitrary code execution was found where eval was used for JSON parsing. In this example, it would be fairly easy to write a code parser to find such issues. But a larger issue would be the consideration to run all those at scale, to run it on every external library used, and every version that was used, is used, or will be used in the future. Finally, we also find several transitive issues through the data, and there are many more, and we can go on for a day. At this point, you would probably have a better understanding of the risks. So I'll be sharing some of our key observations from processing these data. From the examples, we have noted that third-party dependencies are vulnerable to the same type of code flaws and faces the same issues of fixing transitive issues. By keeping frequently up to speed on the data that matters, we are able to discover and act on these issues earlier. Now you might be wondering, apart from malicious code introduced by social engineering attack, how serious can this get? Well, to emphasize on the issue at hand, we have seen new classes of highly critical vulnerabilities uncovered from time to time and affects existing code which may be widely used in today's application. Deserialization issues such as those in JSON data binding, arbitrary file overwrite through unzip functions, the issue of prototype pollution, these have all been observed to be widespread when they were first discovered. And as the number of libraries are expected to increase with time, it is also much more probable that newly discovered flaws can affect even more applications. So to really be safe, we have to know what we are using, whether they have known vulnerabilities, and to actively keep up with this, as a new flaw may be discovered at any point of time in the future. Now that we have a sort of baseline on what information is out there, we can also think about taking the approach a step forward by discovering similar vulnerabilities in other libraries. While this is still an ongoing work in progress, the general concept is to be able to automatically sync out potential libraries that may be vulnerable to an existing vulnerability type. Further, for each pattern, we could come up with a key signature to automatically create a proof of concept and to test if an application or third-party library will produce positive results. It is like running a targeted dynamic analysis scan, and it may not be possible to automatically create a proof of concept for all known types of vulnerabilities. To conclude this talk, we have 3 points to make. So we have to continuously be on the lookout for issues in our dependencies. The number of dependencies increases over time, and so does new types of vulnerabilities. Code that may look secure today may actually be insecure in the future. The machine learning approach is not self-sufficient and can still be improved upon. And that what we have discussed today does not cover all actual prevailing vulnerabilities. So at the very least, we should try to be on par with already disclosed known vulnerabilities while we continue to discover more vulnerabilities through different methods. I hope we have brought across the idea of how we can discover vulnerabilities quicker for a faster response, to learn from what is out there, and to develop an intuition to finding similar vulnerabilities that are out there. Thank you.